So we are in the middle of a series of 4 talks on the astrophysics of black hole binary formation. And I wanted to start with a little cartoon summary of where we were yesterday and where we are going with my talk today. So these are cartoons, but they're not artistic impressions cartoons. They're actually based on real calculations. On the left is what was covered in the last 2 talks at the end of the afternoon yesterday. So this is the traditional binary evolution formation scenario on the left, which goes through common envelope phases, or at least one common envelope phase. On the right is the newer version, which does not involve a common envelope, so-called chemically homogeneous evolution that Selma Domink talked about. And here on the right is what I'm going to be telling you about. This is the sort of complicated dynamics that takes place involving black holes in star clusters. I'm going to focus on globular clusters. Globular clusters are very important in this story for a specific reason, which I will explain later. Smadar Naos later will talk about other systems, in particular galactic nuclei, so larger star clusters. I want to start by setting the stage and contrasting these two a little bit. So the 2 speakers at the end of the day yesterday were very fairly, I think, describing to you the many uncertainties and the many difficulties in these binary evolution scenarios. And the first point I want to make is simply that to most people this looks very natural and very simple and very straightforward, while this, especially if you haven't looked closely or read the papers carefully, looks very complicated and weird and difficult. It is, in fact, really the exact opposite. Binary evolution can lead to binary black holes that merge, but there are lots of difficulties along the way and a lot of fundamental uncertainties in the physics, things that Ilya, for example, referred to as magic wands and parameterized uncertainties, common envelope phases with 15 question marks across, etc., etc. Here, on the other hand, the physics is really incredibly simple. It looks complicated. Black holes go through these long series of chaotic dynamical interactions. But really, the physics is just simple gravitational n-body dynamics. And it's even, to first approximation at least, just Newtonian physics. Okay? Especially in globular clusters, velocity dispersions are of order 10 kilometers per second. That's very non-relativistic. So really all we need here in terms of basic ingredients is to start with a certain number of stellar black holes within a star cluster. Those are the starting ingredients, and then the physics sort of takes care of itself and is almost, in a sense, inevitable. And out of this dynamics come out LIGO sources, as I will show you. So still as a preliminary, since I just told you the basic ingredient is to have black holes in a star cluster, I'm talking about globular clusters here. So let me say a few words about why it's reasonable to say that there are stellar black holes in globular clusters. This has a very long and painful history. Those of you who follow this know well. I obviously won't have time to tell you all about it. Let me just say that as of now, there is very good and rapidly growing evidence observationally for the existence of stellar black holes in globular clusters through observations of accreting black holes in X-ray binaries, but also, this is very recent, a paper that came out just a few weeks ago and I think hasn't received enough attention. The very first determination of the very first dynamical mass measurement for a black hole, a stellar black hole in a globular cluster. This is based on MUSE data, and the minimum mass, m sin I, for the dark object is 5 solar masses. So that's really the gold standard in terms of establishing that something really is a black hole. Certainly stellar black holes are expected theoretically to form in large numbers in these systems. If you take anything like a reasonable stellar IMF, you expect something like 10 to the minus 3 black holes per star. So if you have a typical globular cluster that started maybe with of order 1 million stars, you expect roughly 1,000 black holes, or maybe up to a few thousand black holes in very large clusters, and at least a few hundred even in small clusters. We now believe also, based on current understanding of core collapse and kicks, that most of these black holes, and this is in contrast to neutron stars, most of the black holes will be initially retained in the clusters. And we also now understand theoretically, and this is very recent, that in many cases the clusters will in fact retain these black holes for very long times, all the way to the present in many cases. And that's of course good, because we want to be able to explain why some are seen in globular clusters today. In fact, some clusters retain so many black holes, and this is again very recent work, that we now believe in fact that, at least in many cases, the black holes actually play a key role in determining the overall dynamical evolution and the current observable structural parameters of the clusters. They play a very important overall in the dynamics of these systems. Key physical processes here address basically in a very direct way the two challenges that Selma de Mink mentioned in her talk yesterday. The separation challenge, that's the difficulty in getting two black holes to be close enough at the end that they will actually merge in a Hubble time. And the mass challenge. How do you get two black holes to be 30 solar masses in a merging binary, like many of them we're seeing now detected by LIGO? So these are both very naturally solved through these dynamical processes. Black holes that end up in binaries go through these many interactions, and the classic thing that these interactions do is they tighten the binary. This is the process usually called hardening, and it's very simple. It's been very well known, very well studied for decades in the context of star cluster dynamics. So binaries naturally get tighter and tighter and tighter as they go through this succession of very often hundreds of these dynamical interactions. And then you also naturally, through dynamics, pick out the most massive black holes that are available out of whatever formed in the cluster initially. That's through, again, two very simple physical processes. Mass segregation, which makes the most massive objects in the cluster, including black holes, get to the center of the cluster just through dynamical friction first. Hence, they are preferentially going into these dynamical processes because they're near the center of the cluster where the density is highest. And then also many of these interactions involving a black hole and a binary black hole and a single one or two binary black holes lead to exchanges, meaning for a little while you have three objects or four objects undergoing a complicated chaotic interaction. Typically that spits out in the end the least massive objects, leaving the most massive ones in the surviving binary. Hence, the most massive black holes naturally get into the binaries that are eventually, typically I will show you, ejected from the cluster and then become LIGO sources. Now this is the key, and if you remember only one thing from this talk, this is a good one to remember. This is why globular clusters play really a very special role in this story. There's something special about them. So here I'm showing you now results from a large number of simulations. And for now, we're looking at clusters of a given mass. These are clusters that start with about 200,000 stars, so they're rather small clusters. And I'm showing you results for two different sizes of these clusters in terms of the viral radius, 1 and 2 parsecs. Now it turns out real clusters span a relatively small range of sizes, factor of few in terms of typical radii, but a very wide range of masses covering orders of magnitudes. So what really matters here is the mass of the cluster more than the size. And what's shown on the left is the distribution of black hole binaries that are produced in these clusters dynamically. And the final distribution corresponds to binaries that eventually are ejected from the clusters. So this is where the story terminates. As the binary black holes go through these dynamical interactions, they get tighter and tighter. As they get tighter and tighter, the interactions also tend to kick them. They recoil more and more. And eventually they recoil enough that they leave the cluster. And then the story has ended. And at that point, you ask the crucial question, is that binary now tight enough that it will merge in a Hubble time and become a LIGO source? Okay. So here's the distribution of final semi-major axes. It has a characteristic peak. That's because there is a characteristic energy scale in this problem. The recoil in a dynamical interaction is typically comparable to the orbital speed of the binary. Therefore, as the binary gets tighter and tighter, the recoil gets larger and larger. And basically, this size is set roughly by saying that the orbital speed of the binary is comparable to the escape speed from the cluster. So clusters with deeper potential wells produce tighter binaries naturally. So for a given mass, a smaller cluster has a deeper potential well, produces binaries that are a little tighter. The width of this distribution is typically about an order of magnitude. But if you now convert it into an in-spiral time, a merger time for that binary, you get a much wider distribution. This is now a cumulative distribution, covering many orders of magnitudes. That's, of course, because the merger time goes like the fourth power of the initial binary semi-major axis. And here you see I've drawn this red dotted line here at about a Hubble time to guide your eye. So the binaries that are just right have merger times comparable to a Hubble time, a few gigayears at least. In this case, you have a cluster that's relatively small, so it has a shallow potential well, and it does not harden its binary black holes enough. Hence, you end up with mostly very wide binaries ejected with merger times that are many Hubble times, hundreds or thousands of Hubble times, and those are not good enough to become LIGO sources. Now, as you go up in mass, and this is now scanning the relevant range here. This is on the right, the mass function for globular clusters. This is straight from the Harris catalog. We're here now on the low side. And if you start going up, you see distributions shifting exactly the way you expect. So as you go up in mass, you now have a deeper potential well. The binaries get tighter, and therefore the merger times get shorter. And if you keep going, we're now near the peak, and now we're past the peak. And I'm not going to show you anything for way past the peak because these become extraordinarily expensive n-body simulations for very, very large clusters. But you've seen already the key result, is that right around here, meaning the most typical global cluster, corresponds to this line where the 50% point is right on the red line. In other words, global clusters have a natural scale in terms of the depth of their potential well, which is just right to produce LIGO sources. They're not too wide, in which case they would never merge. They're also not too tight. Too tight is also a problem because these are old systems. And so if the binaries get hardened too much, they merge very quickly, and that means they merge at high redshift where LIGO cannot see them, at least not yet. Okay. So this is why global clusters are so special in this story.
Can I ask? I mean, this includes the coevolution of the binaries with globular clusters.
Of course, yeah. This is all self-consistent simulations. The one caveat, since you want to bring up one, is that this is only true for old systems that have formed all their stars a long time ago, like globular clusters. If you have continuous star formation, as you have in larger systems, galactic nuclei, particular nuclear star clusters, then of course the problem of having binaries that merge too quickly is not there anymore because you can form them recently. Okay. And that connects to what Smadar Naos will be talking about later. Okay. So the obvious question now for many of us has been for a year or two already, now that we have detections, how are we going to be able to tell the difference between these various formation scenarios? And here I have a number of obvious questions you might be asking, and this is really general. You could ask these questions about any formation scenarios or any two that you want to compare. So obviously you might ask, what about predicted merger rates? We now have an empirical rate from LIGO detections. You should ask obvious questions like, does that particular scenario produce enough merger sources? Or maybe is it too high? And do different scenarios predict different things for merger rates? You can look at black hole masses and mass ratios. You can look at eccentricity of the binaries. Here the problem obviously, as was mentioned several times yesterday already, is that as binaries in spiral, the eccentricity gets erased through gravitational wave emission. So the question really is there ever a residual eccentricity that is detectable? And then finally, spins of black holes might be different, in particular their orientations. Again, this was mentioned yesterday already. So here's my quick summary of the answers to these questions for this specific comparison of the classic binary evolution type formation channels versus dynamical formation in star clusters. In general, I think merger rates are really not the way to go. They are extremely uncertain. I personally would never believe a theoretically predicted merger rate, not even my own. And the error bars on the empirical rates are still very large as well, and so I don't think this is particularly promising. Masses and mass ratios, perhaps after we have hundreds of detections, you might be able to see subtle differences between different scenarios, but here the problem is very obvious. Masses of black holes and of remnants in general are primarily determined by metallicity. And so that's true for all scenarios. It's the same. If you're in a high metallicity environment, you will tend to get lower mass remnants. If you're in a low metallicity environment, you will tend to get more easily the higher mass black holes. And that's true for everybody. Eccentricity, maybe. There's a way that even LIGO might be able to detect eccentric merging black hole binaries. I'll turn to this in a minute if I have time. But definitely with LISA. Again, this point I think was made yesterday already. The binaries that are detected by LIGO very often have crossed the LISA band earlier. They do that when they were still wider, and therefore there's a better chance that when they were still wider, they had retained more of their original eccentricity. I will show you an example of that from a real calculation in a minute. And then I think the most promising, in spite of what Ilya said yesterday, because I believe in some of the spin measurements that were made in black hole X-ray binaries. I would like to think that naturally the magnitudes of spins for black holes are large. If that is the case, then spins are definitely the most promising. And it's because of the obvious difference that dynamics, any kind of dynamical assembly predicts randomly oriented spins. Through all this chaotic dynamics, you basically get an isotropic distribution of spins in the end, while binary evolution always retains, no matter how much you tweak all the parameters, or not fudge factors, parameters in the population synthesis predictions, you always retain some strong preference for alignment. So if the spins are large, that means large enough that LIGO can actually detect them. We will know soon what that orientation is, at least statistically. I have about 5 minutes to show you a few more details about all this. So first, spins, to remind you, I think this was said or hinted at yesterday already. I'll start with the spin since I think that's the most promising, at least for the near future. So this is what we know currently in terms of observations. Remember, the only parameter that captures something about the spins, the black hole spins, that's measured from the analysis of the waveforms is this chi effective parameter. This is a measure of projected black hole spins projected onto the binary axis. And it's normalized like a Kerr parameter. So 1 means maximal and aligned spins. -1 is maximal and anti-aligned spins. And 0, which is where all the distributions are centered, unfortunately is one of two things, and we can't tell which one. The spins could be large in magnitude, but oriented randomly, so they're small in projection. Or they have small magnitudes, in which case, of course, they're also small in projection. And at the moment, we can't tell which one it is. But I think with even maybe another 5, 10 detections, we might be getting there very quickly. This I won't go through in any details. This is to make the point comparing directly predictions from dynamics, where the distribution of tilt angle is peaked around 90 degrees because it's isotropic and is completely independent of the mass. and contrast it to various predictions from binary evolution shown in these colored areas here, where you always see, so the median is the edge of the blue zone, you always see a strong preference for a tilt angle near 0, which means alignment. And this is independent of what you assume for kick distributions, etc. You always retain that preference. This is to show you what LISA can do. Here is a comparison between initial eccentricity of merging binary black holes formed dynamically. So the initial eccentricity is, of course, very high. It goes all the way to 1. And this is the final eccentricity entering the LIGO band. And you see these eccentricities are now minuscule when the binary gets to the LIGO band. But with LISA, there's a good chance that these eccentricities, if you can catch the same sources in the LISA band, the eccentricities here would be measurable. So the black lines here show the evolution of the sources that are eventually in the LIGO band here. The black lines are for systems formed dynamically. The blue and green are for systems formed through binary evolution. And you see the black, most of the systems here formed dynamically do cross the LISA band with significant eccentricities that LISA can measure. This is something new, and a number of people have looked at this now in the last year or two. In particular, Johan Samsing, who's here right in front of me, has looked at this in several papers. He has a poster outside, which I encourage you to look at also. And we have a paper led by Carl Rodriguez. I should say Carl is also here. Where is Carl? Carl was my student. He's been a Pappalardo Fellow at MIT for a couple of years now, and he's done, I would say, most of the work that I have talked to you about today. Very recently, Carl has started doing our very first fully post-Newtonian simulation of cluster dynamics. And the post-Newtonian effects you might not think would change much, again, because the scale is so much non-relativistic in global clusters. But during these resonant interactions, where you have 3 black holes or 4 black holes, doing this long chaotic dance, the probability that 2 black holes will come very close together is actually significant. And then post-Newtonian effects can become important, at least in some cases, or at least make qualitative changes in some cases. And this is illustrated here on the right now. So this is what I showed you before. This is from Newtonian calculations. There are 2 things that are new if you include post-Newtonian effects, particularly for very massive clusters, where the binaries tend to be hardened a lot and hence become more relativistic in the cluster. You can get now mergers that actually happen inside the cluster. The binaries are not always ejected before the black holes merge. So this is shown here in this yellowish histogram compared to the blue one, which is for ejected binaries. Those have higher eccentricities, but not sufficient to be measurable in the LIGO band. But then occasionally, you see this little peak here. Occasionally, you get 2 black holes to actually come so close together during 3-body or 4-body interaction that they basically capture. And that's very different, because you have now formed a binary that merges almost immediately. And then it retains basically all of its eccentricity that it had as it formed dynamically during that encounter. And so those can give you sources that nominally have eccentricities really as large as you want, and they almost appear right in the LIGO band, or very close to the LIGO band. Now this poses challenges for detection, which those of you who work on detection should think about. The other thing this does, it was hinted at also yesterday, I think Ilya, in answer to a question I asked, pointed out that if you have mergers occurring in a cluster and the more massive black hole that results from the merger actually stays in the cluster, this requires a lot of luck, because black holes also get a kick because of the merger and the asymmetric emission of gravitational waves at the merger. If that black hole is retained in the cluster, it could merge again. So this gives you in particular what could be a unique signature of dynamical processes. And if you have a mass gap, primordially, say no black holes ever form above a certain mass, 40, 50 solar masses, this is a way of placing black holes above that limit, and you would have that unique signature. Let me not say more about masses, just to make the point again that we can all play with metallicity, and if you play with metallicity, you can get black holes of pretty much any mass you want in the end. In particular here, some people have said that the dynamical formation scenario cannot form low mass systems. That is, of course, not true. It's only true if you limit yourself to old, low metallicity globular clusters. There's a lot of clusters in the universe that are not old metallicity globular clusters, and if you look at younger clusters that do all the same dynamics but have higher metallicity, you can of course get low mass systems. Rates, I won't say anything about, just to repeat that the uncertainties are very significant. This is the currently quoted empirical merger rate, still more than order of magnitude uncertainty. Binary population synthesis predicts, things that are all over the place. This is the error bar you would honestly estimate if you just look at the literature and collect all the predictions. This is doing the same exercise for the dynamical formation scenario. Again, making the point that if you limit yourself to old globular clusters, this must be a lower limit, because there are lots of star clusters that are not old globular clusters. So if you included all star clusters in the universe, I'm sure it would go up, but I can't tell you by how much. Smadar will have some more numbers, I think. And I'll end here, but while we do questions, I'll let this movie run, which shows you what 3 black holes do when they interact.
Okay. Adam? Here. I'll give this one.
In stereo.
This is all fascinating. I have a couple of questions. I'll ask just one.
You've asked one already.
I know. Okay, I'll ask 2. What is the probability that during these types of evolutions that you can accumulate a black hole in the center of a globular cluster of sufficient mass to be interesting in other contexts? I mean, from what you described, it seemed as though it's a very small probability that you'll get up to a significant mass for a black hole in the center. But can you quantify that?
That's right. So for globular clusters, this is not an interesting possibility. The potential well is basically too shallow. There's a very small probability, as I said, that you can grow once. So you could have a first merger. If you're lucky, you can keep the product of that first merger. Maybe you've built now a 60, 70, 80 solar mass black hole. If you're lucky with the kick, that might stay in the cluster. You now have necessarily a highly spinning black hole, though. And the high spin, again, tends to give you a higher kick the next time it mergers. And so it's really very, very low probability that you would go beyond the first step of building up in mass. That's for typical globular clusters where the potential well is very shallow and retention is very difficult. If you're willing to go to more massive systems, and this is really the question, this question you should really ask at the end of Smadar's talk. If you scale up in mass all the way to galactic center type conditions, then of course the probability of retaining products of mergers increases, and you can start building up in mass. And as you know, I'm sure this is one of the classic scenarios for forming seed massive black holes through successive mergers of stellar black holes. So this can certainly happen in more massive systems. Avi and other people here had a paper very recently looking at this formally with coagulation equations, which you can do the calculation semi-analytically in covering a very broad range of conditions. Maybe you want to say a word about this?
Question.
Well, you could advertise your work first and then ask the question.
No, it's okay.
He doesn't need to advertise his work.
I'm not in the business of advertising myself.
No.
So my question is, the smoking gun, that would be the clinching evidence. And as you know, there are limits on an IMBH in the centers of globular clusters, which potentially one can convert into a limit on a cluster of dark objects. It can be fragmented into these low mass black holes. So when you mentioned 1,000, that would be 5,000 solar masses, which is beyond the limits in some clusters.
Absolutely.
So can you comment on that? And also, why don't we see X-ray binaries, as many as hundreds? Or...
Okay, that's a lot of questions. So the last part, why don't we see lots of these black holes in X-ray binaries? We've actually studied this very carefully, and it's in several of our papers. If the center of a cluster is dominated by black holes, you would think naively, well, if there's so many black holes, surely some of them would be visible as X-ray binaries. But that's not true, because they end up dominating the center of the system and the dynamics near the center so much that anything else that's lower mass, in particular what would be the companion, the donor in an X-ray binary, which would be typically a half a solar mass main sequence star, those stars are just not there at all. They're pushed out. Mass segregation is a very strong effect. Center of the cluster would really be more like what you had in mind in the first part of your question, which is essentially just a single dark mass. It's extended. It's in the form of stellar black holes instead of a single intermediate mass black hole, but it would effectively be the same thing. Now, as you said, there are limits on that observationally for some clusters. We are actually studying now, I'm looking at Carl, is studying right now 47 Tuc, which you and others wrote a paper about, claiming there might be an IMBH at the center based on the timing of the pulsars. We think that what you thought was an IMBH could actually be a collection of stellar mass black holes. So we're trying to do this very carefully now with actual fully self-consistent models for 47 Tuc. It's very difficult because 47 Tuc is a very large cluster, and you need to start these models with several million stars, and that is very painful, especially if you need to iterate to get a really good model at the end. So stay tuned.
And Josh.
So my question relates to another potential test, an environmental one. So I'm not sure that the numbers are correct, but if I remember correctly, globular clusters, especially massive ones and with old star populations, are overabundant in ellipticals and in galaxy clusters. And so the question is, if you were in a scenario 10 years from now where localizations of black hole binaries could be at the 1 square degree level, what would the statistics look like for having galaxy clusters be a dominant host population of these systems? Because I think at that scale they could be recognized.
That's a great question, and we haven't looked at that. It's actually a major source of uncertainty for us. So the good thing about globular clusters, as you said, is that we've studied them for a long time. We know their properties very well. We know their demographics very well. So that's good in the sense that we can go from our models that cover broadly the properties of clusters in the local universe and actually make a reasonable attempt at an extrapolation to the whole universe, because we know how galaxies of different types have certain distributions of global clusters. There are uncertainties though, and doing the exercise you just suggested carefully would run quickly into these uncertainties. The big one is we don't know if we should scale with the light or with the mass of the galaxies. And there are opposite claims in the literature. There seem to be galaxies that have very little mass in terms of stellar mass, but still have lots of global clusters. And so that would suggest maybe we should scale with the dark matter mass, the actual mass of the galaxy. The classical way of doing it, though, is to scale with the light. So you would run into this question immediately if you were trying to do the exercise you suggested carefully. But we'll still do it.
Fred, 2 more questions, brief answers. Josh and Ilya.
There's no brief answer to a question that
You can
Josh
always say,
would
I
ask.
don't know.
No, there are, Fred and I have been debating this for years, as many of you know.
You still don't believe the black
No,
holes?
here's the reason why.
Go ahead.
With
I think
the
what you and Carl have done is beautiful work. I certainly believe that if there are black holes, they must form a mass segregated core. What bothers me is that clusters contain significant number of binaries. So now we have mass 2 objects, which also segregate, and we'll get near that core. I find it, until you guys or somebody can demonstrate that you don't, through some exchange collision, capture a main sequence star, subgiant, whatever, from one of these cluster binaries that is going to be close to this subcore and produce what we all would immediately recognize as a black hole system. The problem is that, you know, the statistics are so overwhelming. The neutron stars, despite their escape probabilities and everything else, dominate the landscape. And how can we, with now of order 20 clusters with, at one time or another, luminous LMXBs, not have any black hole candidates? There is one.
That's a long question.
There is.
Complaint. A long question. Yeah.
Okay. The dynamical evidence you mentioned, Fred, is very interesting. I agree. If that stands up, that settles the question. I think that may be.
It's settled.
No.
Look at the Doppler curve.
Look at the paper carefully. The period of that system is not well established. The mass function depends, you know, critically on the period. So it could be, you know, it just needs to be verified. That one system.
Okay, go ahead, Fred.
So there are more parts to the question.
No, the question is, how come there are so many neutron stars and hardly any black holes? Yeah, quick.
Carl will respond to the first part of your question because we have done this carefully, and the answer is no. Those primordial binaries don't get in and exchange and give companions to the black holes. We have done this very carefully. It's in our papers. Carl, please repeat this.
I was actually just going to make a much shorter point, which is that, so the Muse group so far has one black hole candidate. They've got two more, if you believe their papers, they've got two more candidates that they're vetting now, and they're observing something, they're planning to observe something like 20, 25 globular clusters. So they released this one early because they basically got double statistics on it because they observed it twice. So my argument would just be give them a couple of years and we'll have significantly more than one candidate.
I agree. We just need to confirm even that first candidate. That's all I'm.
Oh, that's a fair point. And they still only have essentially one orbital coverage for it. So at least the RV people I talked to said they would be much happier if there were, you know, several observations of it.
Can I say one last thing? Most global clusters do not have obvious neutron star systems of any kind. The global clusters that would be dominated, where the core would be dominated by black holes, tend to be puffy, large core radii. And our models predict those should not have large numbers of neutron star X-ray binaries, radial millisecond pulsars, simply because the black holes dominate the center and basically prevent the much lower mass neutron stars from coming in and doing the sort of dynamics that we know leads to lots of millisecond pulsars and X-ray binaries.
M15 has a very compact core and it's full of millisecond pulsars.
And for sure,
I think we should keep this for the coffee break.
and for sure
Ilya
has no more than a handful of black holes.
Ilya is dying to ask 1 minute for both question and answer.
Okay, so in general, in order to describe the final outcome of a system, you need to have two things. You need to have a description of the evolution, and you need to have a description of the initial conditions. Now, I think, Fred, you've argued, and I actually generally agree with you, that the evolution is more straightforward for dynamics than it is for isolated binaries, although you have the extra complication that you have to involve a million objects and not just two objects, and as the fact that your group has, let's say, improved your results over the past 5 years relative to the way that they had been 15 years ago shows it's not a trivial problem. But I think the big issue is the initial conditions. And there, I think we know a lot about binaries because we can see what massive stars look like in binaries when they're born, and we don't actually know the initial conditions for globular clusters when they formed 14 billion years ago. And I think that's a serious problem that does need to be addressed as well.
Two quick points to answer this. So first, I never said this is a trivial problem. It's easy in the sense that the physics has no uncertainties. It's physics we know how to do. It's computationally very challenging, though, and very expensive. So certainly not trivial. That's one point. Second point is chaotic dynamics, as you all know, erases initial conditions. This is one of the things that's wonderful here. Most initial conditions we absolutely don't care about. Within about a relaxation time, The cluster has completely forgotten any memory of its initial conditions. However, for black holes specifically, there's one very important input that you can never erase, and that's the initial mass spectrum of the black holes, which Stan will give a talk about this afternoon, I think. That's an input for us. It's, of course, an input for everybody. We need to include that stellar evolution physics and know what black holes are formed. Whether it's in a binary or in a cluster, that's always an important part of the story.
And the initial mass and initial size of the cluster?
It's okay. I think you should continue this over coffee. Let's thank Fred.